Hello, everyone. This is Jim Chastain with EasyPower. Welcome to the EasyPower Thursday Technical Webinar. Our guest speaker today is Paul Steciuk with Northeast Power Systems, Inc. And Paul's taken the time to record the presentation so that we can play it. He will be online and prepared to answer questions that you can enter through the chat box or the question box as we go, and then we'll answer as many questions as we can at the tail end of the presentation. Again, thank you very much for attending. So let me hand this over to Paul, and I hope you enjoy the presentation.
Hello, everyone, and welcome to this EasyPower webinar. My name is Paul Steciuk. I'm a co-founder of Northeast Power Systems, a leading supplier of metal enclosed capacitor banks and harmonic filter banks. Today, we're going to speak of the myths in regards to medium voltage metal enclosed capacitor banks and harmonic filter banks. There's a lot of misinformation surrounding the design and application of medium voltage metal enclosed capacitor banks, filter banks. This webinar will discuss various misconceptions from cost to design to application and operation of medium voltage metal enclosed capacitor banks and harmonic filter banks. So it's a fact or fiction type of presentation. I present a statement and we determine if it's fact or fiction. So first, a little bit about Northeast Power Systems, NEPSI, N-E-P-S-I. We were established in 1995. We're based in Queensbury, New York, which is just about 3 hours north of New York City. We're a manufacturer of medium voltage metal enclosed capacitor banks, harmonic filter banks, and other reactive power solutions at voltages between 2.4 kV and 13.8 kV. This is our sole product, metal enclosed systems, and it is what this presentation is about today, to talk about the myths that surround this product offering and also reactive power solutions in general at the medium voltage level. In addition to manufacturing metal enclosed systems, Northeast Power Systems also offers services in startup and commissioning, as well as maintenance. We do power system studies, but only studies to provide support for the products we sell. So primarily medium voltage metal enclosed systems, harmonic filter banks, they require harmonic studies and motor start studies. Motor start studies are performed to support the ActiveR solution. It's a relatively new product, about 5 years old, which involves fast switching capacitor banks for starting large motors. This is an alternate solution to starting large motors. We're in a typical instance. Nowadays, firms are using VFD drives and reduced voltage soft starts to start motors at the medium voltage level between, say, 1,000 horsepower all the way up to 25,000 horsepower. This fast switching capacitor bank is offered to support the reactive power requirements of those large motor starts at a fraction of the cost of a VFD drive, and also at a fraction of the complexity and the cost. So on to the presentation. If you want to know more about NEPSI, go to www.nepsi.com. There you will find a host of information, videos, tech notes, how-to videos, calculators, spreadsheet tools, you name it is there as a technical resource that we offer to our customers. In particular, for those involved with doing harmonic studies, we have spreadsheet tools for designing harmonic filter systems. The information that those spreadsheets put out can be directly used as input to the EasyPower program. So just briefly, the picture on the left shows a metal enclosed harmonic filter system. This system comes with all switching, all protection, all control. This is a C high pass filter system consisting of 2 stages. It's located at a wind farm in northern Quebec. It comes with, it was roughly rated 16 megavars, and it had SF6 switches in there for switching the stages. It had iron core reactors for tuning the capacitors to the 4.7th harmonic. That incoming air disconnect switch, ground switch. The stainless steel boxes you see on top are resistors. So it's a packaged solution. And this is essentially what NEPSI builds at our factory in Queensbury, New York. On the right is an open rack solution. It's an alternate form of the metal closed solution on the left. Okay, and this system typically comes piecemeal. It requires assembly in the field. It's often not integrated like the systems sold by NEPSI. And as you can see here, everything is built at a height of at least 3 meters, 9 foot 6 inches, and therefore you need lift trucks and things like that. They utilize air core reactors, where in the metal flow system we use iron core reactors. So that's primarily the main significant difference between the metal closed system and the open rack system. Here's a couple pictures of our systems. This first one was shipped to South America, rated 54 megabars total. You can see it's a relatively large system. This had a length of roughly 120 feet, so about 40 meters in length. Very large system. This is a copper concentrator plant. Down on the bottom, we also show another large harmonic filter system consisting of 3 banks, each of those rated 75 megabars, 5 stages. So this represents, I would say, the large end of the products. We do sell smaller harmonic filters, those at the 4, 5, 6 megabar range, but all medium voltage, 2.4 to 38 kV with impulse levels between 60 kV and 200 kV BIL. So the first myth we're going to talk about is we're going to talk about detuned harmonic filter banks. It's often thought that if you purchase a detuned filter bank, you don't need to worry about harmonic overload within the filter itself. You don't need to worry about overheating. You don't need to worry about resonance concerns or capacitor failures, and that they're less expensive than tuned filters. So we're going to talk about the difference between 4.7 tuning and 4.2 tuning and some of the myths that surround this. So what you're looking at here is a gas plant. It's a project that we just recently did a study on. You can see here in the circles in yellow, you have a 4-stage harmonic filter bank. We would have a choice to either tune that to, say, 4.2, or call it a detuned filter, or tune it to 4.7 harmonic, 4.8, 4.9, something like that, called a tuned filter. Incidentally, I consider both of these systems tuned systems. When you put a capacitor in series with a reactor, and you size that reactor to tune the capacitor reactor combination to a frequency, it's tuned. But there is some engineers out there that like to differentiate the lower tuned filters, those around 4.2, as detuned filters. So here on this slide, I'm showing 2 impedance scans. The top impedance scan is for a tuned filter. Basically, the impedance drops down to a low value at the tuning point, which in this case is 4.7, and then we rise back up in frequent impedance as we go up in frequency. So on the left axis, we have ohms. On the right axis, we have harmonic number. On the lower impedance scan here is a detuned filter. Really, the impedance scans look the same if you think about it. The only difference is the low frequency point here. In this case, it's 4.2. So you might ask, well, how did I get this curve? I think it's worth mentioning, since this is an EasyPower webinar, is after you go into harmonics mode, you open the switch at the filter and you double click the bus. I have set the system up under harmonic options such that we're using a 1 amp injection, and I set the plot up so it plots ohms, and then that way we have a plot of impedance. You can pull the window over in EasyPower and come up with the actual value of ohms here at each frequency. Okay, so if you kind of study the curves here, we both have a scale of 10 ohms. You can see that they are only slightly different in value. To the left here, I show the diagram for a notch harmonic filter or tuned filter. If it's tuned to 4.7, again, we're calling that a tuned filter. The reactor and capacitor have a frequency tuning point of 4.7, 4.8, 4.9, right? and a detuned filter would be 4.0 to 4.2. So the objective here of tuned filters and detuned filters normally is to supply reactive power. That's the first thing. And they both do that. The only difference is the choice of reactor impedance. And basically, we take XFC and we multiply by 1 over n squared. Okay, and that comes up with where n is the desired tuning point. So if you study the equation just a little bit, you will see that lower tuned filters have a higher reactive impedance, and higher tuned filters have a lower impedance. So what does that mean? If it's a 4.2 tuned filter, it means we have more impedance associated with the filter branch. It means we have more voltage drop across this component at 60 hertz. And subsequently, it means that this reactor has to grow in size because we're supporting more voltage across the reactor. A fifth tuned filter would be 1/25th, right? 1 over 5 squared, 1/25th. The reactance would be a smaller value, and the 60 hertz current through it is the same, but yet we have a higher impedance, so therefore, no, a lower impedance, sorry, and therefore we have a lower voltage, so that reactor becomes smaller. So in general, a statement can be made that higher frequency tuning results in smaller reactors, at least from the fundamental current standpoint. When we're looking at it from a fundamental 60 hertz value for 60 hertz systems, the core of this reactor, if it's a higher frequency, can be made smaller. And that's a key point to consider when looking at the cost of a detuned filter versus a tuned filter. Detuned filters, you're paying more for the iron core reactor if you consider 60 hertz current alone. The capacitor values are relatively the same, whether it's a detuned or tuned filter. So we go back to this slide first, and we note that if we're sitting at this bus, harmonic current injected from these drives here have a choice. Okay, they can flow back towards the source, or they can flow back into the harmonic filter. We can represent this system here with just basically two impedance values, a source impedance here and a filter impedance here. So back to this slide, we have our harmonic filter here. It's an equivalent impedance of the filter, and we have our impedance of the source here. So harmonic current injected from the VFD drives or nonlinear loads are ideal current sources, and therefore the current that's injected here, when it gets to this point, has a choice. It either will flow towards the filter or flow towards the source. The choice here, or the value of current flow, is just a current divider. It's that simple. It's a ratio of impedances between the total impedance of the source relative to the total impedance of the filter branch. So I did some calculations here. We're doing the power of some rule, okay, to get a Z total impedance, okay, and we can do this at the fifth harmonic. And I did that for the tuned filter, and I also did it for the detuned filter. Once we know the total impedance at this point, which is a combination of this value and this value using the power of some rule, we can calculate the harmonic current flow into the filter here based upon taking the filter impedance, okay, actually taking the Z5 total tuned impedance value of 0.1237, and then dividing by the fifth filter impedance, which I have noted up here. Okay, and in that way we can come up with a value of percent, or what percentage of current will flow into the filter branch versus what current will flow into the source impedance. So you can see that for the tuned filter, we actually will take in about 76% of the fifth harmonic current. The detuned filter will take in 50%, 50.46%. You could also do this using EasyPower and just do the calculations, but I think it's important to understand what is going on from a circuit standpoint. So the detuned filter also offers a relatively low impedance path for fifth harmonic. And if you think about what's going on here, we look at the impedance curves here, as we go up in frequency, that relative difference becomes less and less. So the notion that a detuned filter does not take in harmonic currents is just totally wrong. It's based upon the ratio of impedances. if you think about the impedance of the source, this can impact how much current flows into this filter branch here. A higher source impedance here means more current flows into your filter. Whether it's tuned or detuned, it means more current will flow into your filter. And this is something to always consider. So there's a notion that out there that if it's a detuned filter, I don't need to do a study. That's totally a false statement. There's also a notion out there that if it's a detuned filter, I don't need to worry about it overloading. And as we noted here, you do have to worry about it overloading. So these are the things that is a misconception. I call it a myth, and it's something that should be avoided. That common notion that this that detuned filter does not need any kind of analysis. So I do a couple more plots here. On the left here we have a 4.7 tuned filter. I've done a summation all here, and I've plotted the currents. You can see that for the harmonic current injection that we have in our plant, we have 42.13 amps flowing out towards the source. Okay, for the detuned part of the project, we have 58 amps here. So I've changed the filters here to detuned, 4.2 tuning versus 4.8 tuning here. You can see that a value of 42 amps flows through the point towards the point of common coupling versus 58. And then if you look at the filter branches, this four-stage filter bank is in service. You can see we have 80.53 amps versus 55.8 amps. So whether it's tuned or detuned, you can see that the filter is actually, whether it's detuned or tuned, both systems are taking in harmonic currents, and the reactors are being subject to harmonic loading, and therefore it has to be analyzed through some type of analysis. I also want to note that there's the bus voltage distortion. Obviously, the tuned filter is going to do a slightly better job in reducing the bus voltage distortion versus the system here on the right, which is detuned. It's at 2.61. So because the filter is slightly less, of course, we got a little bit more voltage distortion for a detuned system. So here we're looking at just I5. We're doing an all source current injection here, all source current injection here. So we're looking at, well, what's going on at the fifth? And remember, this is 4.2 tune. We can see that for 4.2 tune, we have 51 amps of harmonic current. Here, this is only 51 amps to 51 amps at an angle of 0 degrees. Here, we have 76 amps at an angle of just 0.5 degrees. So at the fifth harmonic, even though this is much closer tuned to the fifth harmonic, its difference between tuned versus detuned is not significant, only 25 amps here. So not a lot of benefit from, if you think about what's going on here, not a lot of benefit from the reactor standpoint and the capacitor bank standpoint to go to 4.2 versus 4.7. What have we really saved here? Not a whole lot. And that's really a key point of this presentation. So tuned versus detuned, fact or fiction. I talk about the myths and I talk about the facts. So detuned capacitor banks block harmonics. That's fiction, right? Detuned capacitor banks, like filter banks, offer relatively low impedance path to harmonics. This is actually impacted by the source impedance. The higher source impedance means that both filters will take in higher levels of harmonics. The question is, how much? Detuned capacitor banks are not susceptible to overloading or overheating. We already saw in the previous slides that detuned filters also can take in a significant amount of harmonics. So the statement here also fiction. Detuned capacitor banks prevent resonance. I didn't really show that in the slides, but like filters, detuned filters experience the same exact issues. If you put a capacitor bank or you have cable capacitance in parallel with the filter, you're going to have resonance concerns. You must be concerned about resonance. And finally, detuned capacitor banks are less expensive. I think it's fair to say that the reactor in both situations needs to be designed for harmonic current. We can also say that the detuned reactor at the fundamental frequency must carry more voltage and therefore it must be made larger. So we can tell you that there are many cases where a detuned filter bank is more expensive. For the filter system that I had provided in this presentation here, this filter system here, I can tell you we were at a value of 12.5% higher in cost for the detuned filter versus the tuned filter bank. So it's contrary to the belief, I think, of many engineers, where they thought that a detuned filter system was less expensive. It simply is not. So another question that often comes up is when we're being compared against open rack harmonic filter banks. It's often said that open rack filter banks are less expensive and metal closed systems are more expensive. So we also say that this is fiction. When all costs are considered, including engineering and procurement, integration, site preparation, installation, commissioning, maintenance, liability, the metal closed configuration provides lower cost of ownership. So let's look at metal closed versus open rack, some cost advantages. For a metal closed system, there is reduced procurement cost. What does that mean? When you go to a supplier metal closed capacitor banks or harmonic filter banks, you're going to one supplier. That supplier will then package the equipment. They do all the engineering work, they do all the assembly work, they do all the purchasing work, and therefore on a procurement side, there's just one item being purchased. On an open rack side, it's just simply not the case. When you buy an open rack solution, you're purchasing reactors, capacitors, switches, CTs, a control system, and somebody has to integrate that work. So you have to add cost in for that, and that can be significant. There's also a time issue. Metal closed systems will install in about 70% less of the time period that it takes to purchase and install an open rack system. So from a time standpoint, when time is an issue, always consider a metal closed system. Footprint. The metal closed solution is just 80% less in footprint area. And this can carry a significant cost. And I show by way of example here, a typical 23 kV open rack harmonic filter system for a mine application. The shaded yellow area here represents the amount of area required to install this harmonic filter system. Okay, we compare that to the metal closed solution. We've taken this area here and we have decreased it to just this area here. Where there is a lot of site work, especially up in the mountains, it can become very significant. For this project alone, it was $1.5 million in savings when it came to site prep work and labor costs. So the metal closed solution, just from a site prep courses, site prep standpoint, is much less. Just consider the fact that we have guide wires or shield wires for lightning. You have the concrete work and so on. Significant cost difference. The metal closed system is easier to engineer and procure. We have one vendor. What's key with metal closed systems is that the responsibility of design and procurement and assembly goes to the metal closed supplier. Okay, the metal closed supplier is probably supplying between 100 and 300 systems a year. For an EPC to develop a harmonic filter system using an open air solution, the engineer involved with that project might be designing a harmonic filter for his first time, or maybe he only does one or two a year. So just from an engineering standpoint, metal closed solutions basically eliminate engineering costs from the project. There are other factors in the design for metal closed systems. They're better in the high wind and seismic zones because they're lower profile, they're lower to the surface of the ground, and therefore easier to design for those types of conditions. And finally, there's a long-term cost to maintain a metal closed solution is much easier. Open a door, change a capacitor, very easy. In the open air solution, you have to get up on a bucket truck, or scissor lift. You have to get somebody there to do that. Somebody's licensed to do that. We're trained to do that. You have to put on a harness. So to change out a capacitor is much more difficult. And then finally, shorter lead times. Metal closed systems always have shorter lead times, partly because air-cooled reactors have lead times that are typically in the order of 26 weeks. And then finally, there's always the forgotten details. This is an open rack solution. And if you can look here, there's just a lot of details here. Somebody has to think of all these details. In the metal closed solution, you're buying something that's totally integrated and shipped complete, ready for interconnection. As one example here, there's anchor bolts. If you were to count up the anchor bolts used in this system here, there's over 288 anchor bolts. So the question is, who is going to buy those anchor bolts? What type of anchor bolt would you buy? How long does it take to install those? These are concerns that are often forgotten. And this is just anchor bolts. So a pretty easy concept, anchor bolts, right? But it's something that's often forgotten. So on to the next myth. Metal closed capacitor banks and harmonic filter banks cannot be built to high reactive power ratings as high as those that might be used in open air systems. Fact or fiction? We say fiction. Again, NEPSI's medium voltage metal closed systems share the same rating constraints as open air systems. So the first thing to realize is metal closed systems utilize all the same components as open air systems. In addition to being able to use the same components, a metal closed system also has access to other types of devices. The ABB DS1, for example, is a 600 amp transient free switch. That's an indoor only rated switch. We also have access to fixed and draw vacuum circuit breakers and SF6 breakers. These are all indoor rated devices. So there's a much bigger choice of components for the metal closed solution. Metal closed solutions are scalable, and it's much like an open air solution. If you need 75 megabars, we're going to break them up into stages. The same thing has to be done with open air solutions. The primary constraint in capacitor bank or filter bank size is the switching device and also the reactor rating capability. So NEPSI has built systems as large as 75 megabars in a single enclosure. I showed you a picture earlier that on that 5 stages of 15 megabars. And we've also built capacitor banks up to 60 megabars at 34.5 kV. So pictures, again, close up, you can see not a whole lot of limitation here in rating. 75 megabars serves some of the largest industrial power systems that are built. This is a single bus solution. We had 3 such systems at this project site, so a total of 225 megabars. Down here is a solar power plant. This was located in California, 60 megabars, 5 stages of 12 megabars. So again, no limits in size. There's a notion that metal closed systems run hotter, and people would think about their car. When they get into their car in the summertime, they say, "Wow, it's hot," and therefore they think, well, a metal closed filter bank would be hot, or a metal closed capacitor bank would be hot, because they compare what they feel when they hop into a car versus what an enclosure would have. So they have a feeling that they think that it runs hotter. But the reality is that a metal closed system, the skin of the enclosure reflects the sun away from the equipment. I'm not going to show you here. We have the sun is hitting an enclosure, and it reflects the sun away. The sun is not hitting the capacitors, where the capacitors can absorb heat. Okay, so therefore the capacitors run cooler. And then we force air through the enclosure. So we're isolating the sun away from the capacitors, and we're providing ventilation. Capacitors themselves only have a loss value of 0.05 watts per kVAR. So then in themselves have a very low watt rating for losses. The open air system, I kind of show a system here. It's just a rack of 3 where the sun is allowed to directly hit the capacitors. Here, the solar radiation, a portion of it is reflected into the capacitor, absorbed into capacitor, sorry, and a portion is reflected off. Okay, so we've all tried to pick up metal objects in the summertime when the sun is hitting it and it's very hot, very hot. If you were to put your hand on your car in the summertime when the sun is hitting it, you cannot hold your hand on it. That's because the heat is being absorbed into the skin of the car. Well, the same is true for capacitors. So when you have capacitors that are rated between 50 and 60 C, it's very easy to see that, and the ambient temperature can be as high as, say, 40 to 45 C. It's easy to see that you can exceed the rating of the capacitor. So it's our opinion that metal closed systems allow capacitors to better operate in hot environments. We also have at our disposal the ability to paint the enclosure white, and this is also another key option to keep the system from running warm. We can put air conditioning in if it's desired as another possibility. We have a LinkedIn article that I posted that explains this information in higher level of detail, and we've actually done some simple tests internal to NEPSI to help illustrate the benefits of the enclosed design. So go to my LinkedIn page and check out that article. So the other possibility that's to consider is that for harmonic filter banks, we can do what we call thermal separation. We have components that are rated relatively cool. These include disconnect switches, CTs, PTs. These all have temperature ratings in the 55 to 65 C range. And then there's the high loss components, which include high pass resistors, which run very hot, and you have iron core reactors that run also in the area of 140 C. Typically, iron core reactors have a temperature rating of 220 C, the insulation system. So we have inside our enclosure, we have low loss components that have relatively low temperature ratings in that 50, 55 C range. And we have high loss components, which in the 375 C for resistors, and iron core reactors 140 C. So if I flip to the next page, you can see what we can do. We can separate the high temperature components, here the reactor, here the resistor, into their own compartments, and allow those compartments to run hotter because that's where the losses are. And then we can put capacitors in their own compartment and run those at lower temperatures. So these components are low loss components. Put a fan in here. It does not take a whole lot of effort to keep the temperature of those capacitors within their rating. For the reactor compartment, we also put a fan. There's higher losses in this compartment, but these losses equate to heat generated in this enclosure and temperature in this enclosure section. But this enclosure section is separated from the capacitor compartment. So I have a separation of devices, and therefore they all operate within their temperature rating. Another benefit of the metal closed design. With an open air system, you're subjected to solar radiation, and you can't get around that. All right, there's a notion that metal closed capacitor banks are less reliable than open air harmonic filter systems. And again, this is not a true statement, it's fiction. The metal closed solution in years past, and I'm going back maybe 25 years ago, there was some quality, I guess there was some reliability concerns. This is back right when we got into the industry. Iron core reactors were overheating and failing. So there are a lot of old-time engineers out there who had experienced this issue. And really what was going on at the time is that the iron core reactor suppliers did not understand the impact of harmonics on their reactors. They didn't understand how the harmonics heated the iron cores up. The designers of the harmonic filters did not account for enough margin in their design. And as a result, there was an abundance of reactor failures. I'm saying going back to the 1980s. But if you go forward to the present day, the reactor suppliers who are in the business have many, many years experience, and their ability to build a reliable reactor is not difficult at all. In addition, the metal closed system had other benefits from a reliability standpoint. The enclosure itself protects the internal components from lightning, Faraday cage effect. The enclosure protects against birds and snakes and wildlife, so there's a prevention for flashover within the enclosure. We also protect the internal components from dust, rain, snow, ice. We've done avalanche designs, earthquake, we're a seismic 4 zone, and then airborne contaminants. We can protect the internal components, those energized live parts, from those contaminants. Inadvertent operation of the system is a common cause for failure. A metal closed system is typically key interlocked. We force a sequence of operation. We force a sequence to get into the equipment, and therefore we prevent misoperation or misoperation, which can lead to failure. There are other options too: active arc flash mitigation, and this would be through an ABB ultra-fast earthing switch, for instance. If there is a flashover within the enclosure, we can clear that fault within 4 milliseconds, basically eliminating any damage from the arc blast. And in so doing, it allows the maintenance people to go into the equipment to replace the failed component and then to re-energize the system. So active arc flash mitigation is something that's available in metal closed systems. And then finally, we can provide advanced protection schemes. It's very typical metal closed systems are equipped with multifunction relays, digital relays, and advanced protection systems that allow for individual as well as THD harmonic detection for overload. We provide over temperature inside the enclosure, and therefore it can protect against over temperature also. So many different control and protection features that are available to help keep the system reliable. Next myth: medium voltage metal closed systems require specially trained maintenance people. Our systems and most metal closed systems are designed to be maintained by maintenance people who have a knowledge with maintaining medium voltage switchgear. So if the maintenance people can understand and maintain medium voltage switchgear, they can maintain a capacitor bank or harmonic filter bank. It does not take a especially trained maintenance person to maintain metal closed systems. They're designed for that purpose. So iron core tuning reactors that are used in metal closed harmonic filter banks are not reliable. And I kind of touched on this already. The key to ensuring that an iron core filter reactor is reliable is to make sure you specify it correctly. NEPSI takes a position that the fundamental current rating of the filter should be multiplied by 1.35 to 1.5. There should be a significant margin at the fundamental. And then the harmonic current rating should not be based on just the study, but then also based on having a significant margin between what your study has determined to be the harmonic current and what the rating of the reactor is going to be set at. And I'll kind of give an example. If I have a reactor that's rated 100 amps of the fundamental, in other words, it has a reactive power rating equal to 100 amps, we would design and request the reactor supplier for a reactor that had a rating of either 135 or 150. And what that does is it forces the reactor supplier to put iron into the design and to basically design in reliability. At the harmonic, if for example at the 5th harmonic with a 5th tuned filter reactor, maybe your harmonic analysis determined that your harmonic current would be, say, 30 amps. So remember, fundamental 100, we calculate 30 amps. 30 amps at the 5th harmonic. We would not design that reactor for 30 amps. We would most likely design that reactor for 60 amps. In some cases, depending upon the type of system, we might even go up to 100 amps. So we could set the reactor harmonic current rating equal to the fundamental harmonic current to the fundamental frequency current that's expected through that reactor. So again, we're adding significant margin into the design. And in so doing, what we're doing is we're reducing the noise that the reactor will produce. We're reducing the losses that the reactor will produce. Losses vary by 1 over the current squared. Okay, so if you're at say 80% of its rating, you're already at 64% of its total heat capability. Okay, so it's important to put margin in the reactor. If you do that, the reactor will be very reliable. A iron core reactor, another point to be made is iron core reactors in many ways are built in the same fashion as air core reactors. The only difference is the iron. In an air core reactor, they wrap the winding around an aluminum structure, and air is the magnetic path for the magnetic field. For an iron core reactor, the winding is wrapped around the core rather than around that aluminum structure, and the iron forms the structure for the iron core reactor, but it also provides a path. Both the iron core reactor and the air core reactor are posted up on insulators, so the insulators bear the primary voltage stress in the system. The voltage across the reactor is just 1 over N squared, okay, times the line to neutral voltage of the system. So a 5th tune reactor at 8 kV at 7960 line to neutral, which would represent a 13.8 kV system, will be just 1/25th. Okay, so on the order of say 500 or 600 volts, not a whole lot of volts across the iron core reactor. So therefore, under normal conditions, it's just not stressed. So on to the next myth. Okay, I see this often. If my harmonics are low, I do not need to purchase a harmonic filter. I only have 1% distortion. Factor fiction. Okay, the answer is fiction. Okay, we hear this all the time. It is an over-applied rule of thumb developed in a low voltage marketplace. Okay, it's simply just a false statement. Low-level harmonic currents can be amplified to very high values when they flow into resonant circuits, such as that which exists between a shunt power capacitor bank and its source impedance. So we so often hear a customer say, well, I only have 1 or 2% distortion, so I'm just going to install standard capacitor banks. This is just not the case. If you were to just develop a very simple case in EasyPower, put a capacitor in the system and have it resonate with the source at the 5th harmonic and inject just 1 or 2 amps, you would see that the amplification can be significant enough to cause voltage distortion to exceed 5% and cause you to exceed IEEE 519 limits. So again, relatively low distortion does not make a difference. If you have low distortion, you don't need to install harmonic filters, but if you have plans to install power factor correction, even a few % distortion, you need to consider resonance in the system and determine if resonance is going to be an issue. This kind of is an extension of the statement I just made. I hear this all the time also. I purchased only 18 or 24 post drives. I can install standard capacitor banks. So somebody goes out, they spend extra money on 18, 24 post drives, and they say, well, I can buy capacitor banks now. I don't need harmonic filters. Again, simply not true. 18 and 24 post drives will put out 5th and 7th harmonics. Yes, under ideal conditions in a laboratory, 18, 24 post drives do not put out harmonics, but the reality is that the fundamental voltage is not perfectly balanced. The impedances of the network between A, B, and C phase are not perfectly balanced, and the electronics within the drive itself are not perfectly balanced. So when you don't have these perfectly balanced conditions, a small amount of 5th, 7th, 11th, 13th harmonic currents will be put out. Those small amount of currents can resonate with capacitors in the system and can result in problems. So again, it kind of falls back to the previous question here. If my distortion is low, do I need to consider filters? Yes. If you're going to install capacitor banks, they most likely will still need to be installed as a filter or as a detuned capacitor, but certainly not as a capacitor bank itself without a tuning reactor. So another one is I start my large motors with VFD drives and reduced voltage soft starters. Since they are only temporary, I don't need detuned capacitor banks or harmonic filter banks. Fact or fiction? Okay, so strictly speaking, from an IEEE standpoint, if you're going to start those drives, yeah, you do not need to worry about exceeding those limits. But the fact is that if you have capacitor banks in the system and you're starting those drives or those reduced voltage soft starts during the starting periods, which may last between, say, just a few seconds up to a minute to start those motors, the VFD drive and reduced voltage soft starters are putting out a significant level of harmonics. Those harmonics can interact with the capacitor bank and cause resonance issues. So one thing that NEPSI does do is that we put into our control system a fast trip, and we allow the VFD drive or the reduced voltage soft start to communicate either through the network or through direct communication with an input to our control system. That a VFD drive or reduced voltage soft start is about to start. We drop our system off, and we allow that VFD driver reduced voltage soft start to start, and then the system comes back online and does its power factor correction after that motor start period. The other possibility is just install detuned capacitor banks or tuned filter banks, your choice. But these two types of systems will include resonance in the network. So that's your choice. Okay, cost per kVAR is another myth that we often hear. Can I estimate my capacitor bank and metal close harmonic filter bank based on rules of thumb, cost per kVAR? And we hear this quite often. The customer might call and say, hey, I know my cost per kVAR is this. If I double it, you can expect a double value in cost. And this is simply not true. If you look at the capacitor alone, yes, you can apply a cost per kVAR rule of thumb. But if you're looking at an entire system which contains switching, protection, control, you cannot use cost per kVAR. It just simply is not true. You need to consider all the cost factors. There's also the voltage level, whether it's a filter bank or a capacitor bank, how many kVAR per stage. These are all factors that come into the cost of a filter bank or a capacitor bank. The cost per kVAR rule just does not work. What we tell our customers is if you need a quote and you need it quick, then just call NEPSI. We'll give you that quote within 24 hours. Budgetary numbers can often be given within a couple of hours. So instead of trying to do a cost per kVAR rule, just give us a call. We'll give you a strong budgetary number to work with. So that ends my presentation. I'm going to have an open mic session at this point in time where people can ask additional questions. I hope you enjoyed the presentation. Again, if you want to contact me, it's paul.steciuk@nepsi.com. You can also look us up on our website at www.nepsi.com. Again, there's significant amounts of information there, tech notes, how-to videos, videos on our product offering, case studies, in our product literature. So please check out that site also. And if you have an opportunity to link up with me on LinkedIn, I try to publish at least once every 2 weeks on subjects related to power factor correction, reactive compensation, medium voltage metal close cap banks, and filter banks. So thank you.
Good job, Paul. So now for those that entered a question, I'm going to hand the screen and the mouse over to Paul and let him take up the presentation answering questions from there.
Well, thanks everyone for attending, and so I'm just going to go through the list of questions here. If we generate some more questions, feel free to ask. So the first question that came in is, what's the main technical difference between using a harmonic filter versus a capacitor bank? So what I put up here on the screen is just an impedance scan for a multi multi-stage capacitor bank. So there's 4 stages here. And as these stages come on, you can see that there's a resonant point that exists for the stages. So there's a 0 k-bar line here, the straight red line, which is just a straight impedance line. As we switch on 1 megabars, 2, 3, and 4, you can see that we cross resonant points at the 11.19. We drop down to 7.82, 6.46, and 5.59. So when you install a capacitor bank, you can expect to get resonance at frequencies that start at a higher harmonic and then work their way down towards lower harmonics. When you install a filter bank, normally that filter bank is tuned to a frequency, and you get an impedance curve similar to this. For a multi-tuned filter bank, you get a series of impedance curves, but as you can see here, the tuning point, in this case 4.7, has been pegged at that point. It does not move no matter what size capacitors I bring on, whether it's 1 megabar, 2, 3, or 4 megabars worth of reactive power. That 4.7 filter, the impedance at that point basically remains close to 0 ohms. Below the tuning frequency, though, you can see there's a resonant point that does exist, and that's created by the filter bank and the system impedance, and that does move. This is not of concern here because, generally speaking, there's no harmonic currents at a frequency below the 5th harmonic. So capacitor banks will cause resonance here at various frequencies. Those resonances would result in high voltage distortion and high current distortion in the system. When it's a tuned filter like this, you're going to push your resonant point down below your tuning frequency, and this is one of the key reasons why you tune to a low frequency, is to avoid any kind of resonance above that tuning point. So we always start at low frequency and work our way up from there. So the reactive power output of the filter is desirable usually. That's why you're installing the filter bank in the first place. But the secondary benefit, and sometimes it's a primary benefit, is that you're looking to filter harmonic current from the system. Capacitor bank won't do that, a filter bank will. So there's additional benefits related to a harmonic filter. And it is also worth pointing out that sometimes there's concerns about transients in the network during switching. A harmonic filter actually eliminates that transient concern also. So it's another third benefit that you get from harmonic filters. So next question. Why was the tuning point set at 4.8 or 4.9? Here, I think I've already answered this. What we're trying to do is we're trying to avoid resonance at frequencies above the 5th because there could be harmonic currents at values above the 5th harmonic. So we always pick a value below the 5th. As I showed in the presentation, the further you get away from the 5th harmonic, the less harmonic current that the filter, or that detuned filter, whichever you would want to call it, will take in. But as I showed during the presentation, even a 4.2 harmonic filter or detuned capacitor bank will pull in harmonic current. So the harmonic that you tune to, whether it's 4.2, 4.7, 4.8, 4.9, there is not a wrong answer. It's just a matter of how close to the 5th do you go, and how much harmonic current you will pull in. But you need to be concerned at the 4.2 as much as you need to be concerned at the 4.7, 4.8, and 4.9. It's oftentimes that you tune below the 5th harmonic is very common, 4.7, 4.8. I show in this curve here that there's a resonance here below the tuning point. If you could just imagine sliding this curve slightly to the right, that's what can happen with the tolerances on the reactor. If say the reactor comes in with a lower impedance, it's going to slide that curve to the right. If the capacitance comes in off, also it can slide the curve to the right. And as you fail capacitors, it can slide this impedance, this resonant point to the right. So another reason to tune below the 5th and to provide some margin between the 5th and your tuning point is to allow for variation in capacitance and reactance, so that you do not have an inadvertent resonance at the 5th should this whole curve shift to the right. Okay, so next question was about active filtering. Is active harmonic filter any day better tuned? Okay, let me make sure I got this right. Is active harmonic filter any day better tuned filters? All right, so there's two questions regarding active filters. One is they're asking, is active filtering better than tuned filters? So first of all, active filters are very expensive, but I do think that they have their benefits, and that they're highly flexible pieces of equipment. It's normally a low voltage, not a medium voltage item, and they do cost I don't know, maybe about 100,000 per 1,000 kVAR, so 100,000 per megaVAR. So they're quite expensive at the low voltage level. You could step that up to the medium voltage level, and we do consider doing that. But again, it's a low level. So it's good for filtering low levels of harmonics, I would say, active filters, and they're very fast. They can provide reactive power on a very quick basis also, and it is highly flexible. Some of the units I've looked at have the ability to dial in a range of frequencies for which you want to eliminate. But the use of active filters, you need to be careful if you're applying those in conjunction with capacitor banks. You would always want to have a detuned capacitor bank or a filter bank tuned to 4.7 or below if you're going to supply active filtering with some type of passive reactive power compensation. You asked a question also about filter design. Is it the active filter design? Do you provide margin in it? My understanding with active filters is that if you buy a 250 amp 480 volt active filter, it has the ability to filter 250 amps of harmonic current, and that's the way it works, and that's an RMS value. It's going to only filter up to its rating. So if you purchase 250 amps, you will get 250 amps of filtering, nothing more. The active filter is a smarter device, so it's not going to bring itself into overload. A passive filter will bring in harmonic current no matter what value of current you give it to. So again, it's an impedance divider here, right? How much current flows into the source versus how much flows into the filter. So if you present it more current, it will take in more current and will burn up. So passive filtering, you need to be careful to make sure that you have not exceeded its capabilities. And it's also a good reason why you should be putting some type of protection on your harmonic filter bank, because if the harmonic load in the plant goes up, it may exceed the initial design rating of the harmonic filter, and you could overheat and burn the filter up. So it's important to have some type of monitoring in there. It's also very important to always have ample rating, a significant rating in the filter bank to allow for harmonic load growth in the system. So I guess to some degree, active filtering is nice because it will not burn up if you present it with more harmonics. It will just become not sufficient enough to cancel the harmonic current that you have in your system. They are scalable, so if you increase your harmonic current in the plant, you can also increase your active filtering in the plant. So in any case, it's a technology that's more used at the low voltage level. At the power ratings that we would typically see at the medium voltage level, it's almost prohibitively too expensive. Okay, next question. There was a question, can you, I guess I will repeat it. It was answered. Maybe the audience saw the question. So you can watch these webinars online after the fact. What harmonic impact can expect on reactors installed in the system for the purpose of reducing available fault current of degenerating sources? So oftentimes in the network, they will add, I go back to this one here, they will add impedance into the source. The addition of impedance into the source is merely to add impedance here is to change the short circuit level. You are going to decrease the short circuit level if you add impedance. By decreasing the short circuit level, you will change the resonant point. If you're adding capacitors, you're going to push your resonant point to a lower frequency. So that would be, of course, a concern. If you already had harmonic filters in the system, it would mean that more harmonic current would flow into the filter bank if you were to add impedance. So what you have is, I'm going to slide over to this slide here. If you add impedance here, which is effectively what you're doing, it means you're decreasing the short circuit current. It means that the current divider rule, you're going to push more current into your filter. Okay, so capacitor banks, you're going to push your resonance down to a lower frequency. If you have harmonic filters, you're going to push more current into your filter bank as a result. And I think it's fair to say that you're increasing the overall impedance of the network, so you will have a corresponding bump in voltage distortion within the plant for that same system. Okay, next question. If you use detuned, you get more harmonic current back to the source, so it makes handling the harmonics easier. So again, if you're detuning the filter, what you're doing is you're making this filter less desirable, or a higher impedance path for harmonic current to flow, so more current flows back into the source. So in a sense, you are increasing the path you're increasing the impedance for the fifth harmonic, for instance, into this filter branch. So it is easier, but the question becomes how effective it is. And I think the only way to really understand how effective it is, you have to put the data into a simulation program like EasyPower and determine how much current will flow in the source, how much will flow into the harmonic filter, and evaluate it. What we hear a lot of times for detuned filters is people say and think that analysis is not required. And that's part of what I disagree with, is that the detuned filters will bring in harmonic current, and you need to still evaluate their effectiveness. And they're not always less expensive, as I showed in the presentation. Okay, it says, next question is, what do you consider to be the MTBF and MTTR of open rack versus enclosed systems, particularly for air core and iron core reactors? So first of all, I think it's worth noting that we do have a technical note on our website. If you go to the resource tab here and you click on technical notes, you can scroll down and you can find a technical note talking about mean time to failure in MTTR. For the most part, that type of analysis is not applicable to harmonic filter banks and capacitor banks, because MTTR and MTBF rely upon components that are used in repetition in high numbers, for which you can get statistical data for. It just doesn't, and it also involves having predictable maintenance cycles and things like that. So it's very difficult to come up with an MTTR or MTBF number. And the tech note that I present there talks about this, but we also do talk about failure rate and things like that. And what I can say about iron core reactors is if they're not designed right, they will fail. And the iron core reactor is a little bit more susceptible to failure for not being designed correctly, and that's because of the iron core itself. If you have designed an iron core reactor or specified an iron core reactor, and you have not specified enough current and you apply it to the system, the core may not be able to carry the flux associated with that harmonic current, and it can overheat. Or the winding may not be able to carry that current and then overheat. So there's two components that can fail. For an open air solution, you're using air core reactors, and your only concern is the winding itself. So for a underspecified, what I call an underspecified reactor, an air core reactor might skate by a little bit easier than an iron core reactor. So
Paul,
as I said,
this
yes.
is Jim. I need to interrupt you. We've overran our time slot, and we'll be able to answer any questions that weren't answered online via email. do appreciate very much your presentation, and the information is very good and obviously very useful to the audience. So thank you very much, and we'll have to close out this until next time. Thank you, Paul.
Great, thanks. Thanks, Jim. We'll see you. Thanks, everybody.
Bye.